So, dear students, in this video, we'll be talking about Franck Hertz experiment. We have already talked about uh, the existence of energy levels in an atom using Bohr model, and we have defined some basic definitions like excitation potential and ionization potential. Now, this Franck Hertz experiment is basically a direct evidence to confirm that there is existence of fixed energy levels of atoms. And this Franck Hertz experiment, it was conducted, it was performed in 1914, and and what they did, Franck and Hertz, they performed a series of experiments to measure those excitation potentials of atoms of different elements. And these experiments showed directly that in an atom we have discrete energy levels. So the existence of discrete energy levels was directly confirmed using Franck Hertz experiment. Now, to go with this in a very crude way to see what experiment is all about, is that uh, we have an apparatus which has a tube. Say, I'll draw it. Suppose I have a tube, and it has a gas inlet window, and okay, and it has to be like this. So then we must have some filament that will emit electrons. So for that we will have a supply, and this will be connected to need as a set of supply. Then we have a current meter, and then we have another plate here. So this is the rough diagram that I have been drawing here. So here we have to introduce another piece of voltage, and this is called as grid G, and this is, say, P, and this is my filament F. And from here to here I have voltage V naught. From here to here I have V naught. Here to here I have V. So we have a filament. We introduce some specific gas at some specific pressure. And to talk about this is that we have a glass tube which is basically mounted by a filament over here. This filament is F. We have a grid and plate P. The filament F is heated by making by a small battery, and an accelerating potential V is applied between this F and G. So that potential is here, and small fixed here we have. If you see, I introduced this battery. Here we give a small fixed retarding potential. Its value is nearly 0.6 to 1 volt. So this is between G and P. Now the gas of the element whose atoms are to be studied, we introduce that in the tube through this inlet, and this tube is maintained at a pressure of 1 mm Hg. right? The electrons are they are emitted from they are emitted from the filament when it becomes hot, and they are accelerated between F and G, and the potential that we have between F and G is V, which is greater than that of the potential that we have, uh, the retarding potential that we have between G and P, right? So this plate P is connected with an ammeter where the current can be recorded, and the current that is recorded by performing the experiment, uh, uh, and what we obtain is the current, and this current is plotted against the potential V, which is gradually increased from some zero, uh, from some from some zero voltage. The curves that we obtain by taking the measurements, uh, they so the curves that we obtain from the emitter and plot them, what we obtain is something like this. We have the current, and then it goes down, then it goes up, then it goes down, then it goes up, and then it goes down, and then it goes up. So we can see that we are obtaining some kind of peak. Now, this is my voltage. This is accelerating voltage. And this is the current that is measured by this, that's measured by this emitter. So here I have the current. Now, we would like to draw the dots here so that we can have the. Now these electrons, they are emitted from F, the filament that we have. They are emitted from this filament with a range of small energies. Now, in the beginning, as we start from zero, and they acquire some small additional voltage, say EV, and on reaching this grid, these electrons, when they reach to this on reaching this grid, those electrons whose energy is now greater than this EV naught, they will be able to reach P, and then only then the current is obtained. As this accelerating voltage that we have is increased, more and more of the electrons are arrived at the plate, and the current rises there, right? Now, between F and G, the electrons collide with the gas atoms, but since the electron energies are not enough to excite the atoms, the electrons do not lose energy in those elastic collisions, where they are not able to transfer their energies, because it's not like all the energies that or the electrons that come from this filament will be absorbed by the atoms. That seems to be the case, and between F and G, these electrons, they collide, and there are elastic collisions, and their energies are not sufficient. When the accelerating potential becomes equal to the first excitation potential, we see of the gas atoms that we have here. So here we have the current, but this current is coming by virtue of the by virtue of the elastic collisions, where electrons are not able to eject or excite the electrons of the atoms. Right? This is what I'm trying to say here. So if I call this as VC, and this I would like to call as twice VC, and this thrice VC. So So what happens is that when the accelerating potential V that we have, when it becomes equal to the first excitation potential, that is Vc of these gas atoms, the electron's energy at G that we have here is EVC. At that time, what it has EVC amount of energy. The electrons can now suffer inelastic collisions with the gas atoms near this grid that we have, and they can excite them to an energy level above their ground state. They can excite them to the next they can excite them to energy levels above their ground state. The electrons which do lose their energy and are unable to reach P against the retarding potential, right? So they will these electrons, those electrons which do so lose their energies, the current drops. So they lose their energies because they are unable to reach this P. So in that case, we can see that there is a drop. We can see that we can see there is a drop. Hence, this current drops sharply. Thus, the position of the first peak gives the excitation potential. So this peak gives us the excitation potential, the first excitation potential that I am trying to talk about. Now, as this accelerating voltage or potential is increased further, the electrons suffer inelastic collisions nearer and nearer to the filament F, so that when they reach the grid, once again they acquire enough energy to reach the plate P. The current thus begins to rise again. So now there is again the rise of current. There is again increase in the current, and acquires enough energy, these electrons to reach there, and then the current thus begins to rise, and when V becomes equal to this twice Vc, when it becomes equal to this, a second inelastic collision occurs near the grid, again at this grid. At this grid, we have another inelastic collision near the grid, and the current drops again. Thus, the second peak gives us twice at 2 Vc naught, where we have this small dip in the current. This process keeps on repeating for 3 Vc and so on and so forth. Now the point is that the first peak that occurs at a potential slightly less than that of this Vc. This is because electrons are emitted from the filament with a finite velocity, and hence with some energy. The true excitation potential Vc is obtained by measuring the difference between two successive peaks. And atoms, if I talk about atoms which have more than one excitation potentials, can also have more than one ionization potentials. Therefore, in actual experiment, the curves that would have been obtained, they are quite complicated, and we cannot be in a position to distinguish between excitation potential and ionization potential. Now the point is that the experiment that we have demonstrated here, what it shows is that electrons transfer energy to atoms. Okay, so there are atoms, the gas atoms. These electrons transfer energy to the atoms in discrete amounts, and that they cannot excite atoms if their energy is less than some EVC. So This is what was exploited by Franck and Hertz, and they demonstrated it directly by observing the spectrum of the gas during the electron collision, and they showed using this graph that a particular spectral line does not appear until electron energy reaches some threshold value. For example, in case of mercury vapors, what they found in case of mercury vapors, they found that the minimum electron energy is nearly 4.9 electron volts. So they could not find this thing less than 4.9 electron volts. And they, unless the electron reaches to an energy of this value, and to obtain a line in the spectrum as 2536 angstrom line of mercury, and a photon of this wavelength light has an energy of just 4.9 electron volts. This shows that discrete energy levels do exist. They exist in atom, and the electrons of the atom can exist only in these discrete levels. They cannot exist in the levels which are forbidden, which are not allowed. They can exist only in those shells. So Franck-Hertz experiment was one of the direct evidence of existence of non-radiating shells of atoms.